Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my operating system. It's currently an x86 only operating system that boots in a virtual machine, and it's written in Rust. And so far we support some things. We boot. Big first step for us. We have like memory allocation, so like vectors, maps, those can all come from like heap allocations that happen through our allocator. We have async await support, so we don't have any like threading right now, but we do have support for doing multiple things like at once by using Rust's like async model. We have logging to serial, and we have VGA written here, but that's actually not true anymore. So we have serial logging. We have unit testing. We have RTC support, so like we can like read write the clock, and we can use it as like a timer mechanism to get like monotonic time. We have support for PCI, and through PCI we have Ethernet, and over Ethernet we have the ability to like send and receive packets from like a specific IP. So we have like ARP to negotiate IP to MAC address. We have UDP. We have like TCP to the point where if we don't drop any packets, it works. But there are some cases where our real like retransmission logic isn't quite there. We have enough that we like proved that we can like write a web server and get like run a website from our kernel. And last stream we implemented graphics support of some sort. So we have this demo running right now that is this little ball that's bouncing around, and it's not very fast, right? We're running it like 1 Mississippi, 2 Mississippi, so like maybe like 3 or 4 frames per second, and that's with like optimizations on, and that's like absolute trash, right? Because this is, I think, only a 640 by 480 screen. Let's see, boot. Yeah, it's 640 by 480, and that's like just not good enough. Not good enough at all. So today what I wanted to look at was how can we speed this up? And there's a lot of like obvious things to fix here. So I thought we'd just like kind of start poking them and see how far we get, see how much we need to get done before we would be able to implement something like a game of some sort, right? We want to eventually get to the point where we could render a like window manager or something and like, you know, drag a window around. And if that's not responsive, it will be awful to use. So yeah, that's what we want to look at. So first thing on the list is probably looking at function call overhead. So in our demo, where is our demo here? Here's our drawing demo. So we run this draw circle, and what it does is it loops over the entire screen. So it iterates over the frame buffer height and the frame buffer width, where frame buffer is just like a chunk of memory that like if you write a number in there, it'll like convert into a certain pixel. For each pixel, we check if we're like in a sphere. So we have like a sphere in normalized coordinates, where we say like the formula for a circle is like x squared plus y squared is equal to r squared. So if we are in the sphere, that means that our x squared plus y squared is less than r squared after doing like some offset jiggling, right? This like minus center x, center y. And then we then call set pixel for that pixel using the specific color. And this is like a very poor, like hard to optimize loop, right? If the compiler wants to try to like do a bunch of work at once, not the compiler, sorry, the CPU, it has to like get this branch prediction right, and it has to go through this function call, and this function call does a bunch of like color conversions from like float normalized space to like uint32, and then here is where like the actual work is done of writing to the pixels. So I think that probably what we want to do is we want to see how fast can we like render the whole screen a certain color. And if we get that working pretty good, then we can start like building up an abstraction that does that effectively for what we're trying to do. So we might end up at a place where we have to we might end up at a spot where we have to, what's the word? Draw a circle, like add functions to draw circle, draw rectangle, draw sprite, right? Like we might have to like make special cases just to make the compiler automatically speed things up with like vectorization and stuff like that. But let's just like start by drawing a square. Once we draw a square, then we'll have a good idea of how long everything should take. So maybe the first thing we're going to do is time original function, time, or make an efficient draw rectangle, right? Because we know that if we can draw a rectangle over the whole screen and that's efficient, then we have like somewhere to work towards. And if that's not fast enough, then we're gonna have to like think really hard. But if it is fast enough, then we've got somewhere to go. So here we don't know what we're gonna do after that. It will depend on our initial results. So let's just get going. So we have our like concept of time is driven by this like clock. So let's see. You have like CPU. Oh, CPU. PU. And he's connected over like memory, like, or IO ports. Ports is the wrong word, like IO address space to this like RTC. And inside this guy, how do you draw like inside? We could draw like, we could get really fancy here and draw one of those like, this goes into like a magnifying glass. And we could draw like a little bubble here. Inside here is like a rock of some form, like a little crystal. And when you put like electricity through it, I think it like pulses at like a specific rate based off of the shape of the rock. If I understand clocks correctly, I don't really, right? I kind of made that up, but that's my understanding. There's like the crystal in there, and you put electricity through it, and it gives you like constant time. And every time this like thing goes through its like up-down loop, at like here, or maybe like at the bottom, or maybe like at center, I don't know where, but like at a certain period, this is going to fire an interrupt back to the CPU. And in our case, that's like 256 hertz, which is pretty shit. That's really like an infrequent clock, but like, what is that? 1/256 is 3-4 milliseconds, right? So that's not good, but it's not bad. If we're aiming to like run at like 30 milliseconds, basically what we want to like, if we get to the point where our entire frame is drawing in less than 3 milliseconds or less than 4 milliseconds, mission accomplished. Now it will be kind of hard to start measuring like our optimizations at that point, but that's okay. So what happens, sorry, I got ahead of myself. What happens is this fires an interrupt to the CPU, and every time that this triggers, the CPU goes like, oh fuck, I'm gonna stop what I'm doing right now, and I'm gonna like add 1 to this clock. And so what we want to do is we want to see, we'll like use that number as a measure of how efficient our algorithm is, I guess. So what we can do now is we can maybe start by saying start is equal to the monotonic time, which is what we're using to track. We call this monotonic time. It tracks every interrupt. Every time the interrupt fires, it increments the time in here. We can get the time like this, and here we'll set the end is the monotonic time, and we'll print line what, like draw took end took this in seconds, I guess we'll call it, and we'll say end minus start. This is going to be converted to a float divided by the tick rate. I think it's tick rate. We have a method on here that will tell us tick frequency. So if the tick frequency is going to be like 256, so to go from ticks to seconds, we have n ticks times 256 ticks per second. This is the other way around. So we have to divide it to get to seconds. Little stoichiometry saving us again. So this is correct to divide here. And let's just start by running that. So in debug mode, we're going to wait a second. Maybe wait a lot of seconds. Oh, here we go. You can see it. Oh my god. Oh, it's so slow. What the fuck? Holy shit. That's 12 seconds, 12.9 seconds per frame. That's crazy. If we run and release, we're at maybe like 300 milliseconds per frame, 320. So it's not great either. Now, if we were to do something in here where instead we did like pub function draw rectangle, and we took in, or we'll say, we'll call this function clear, right? And he's going to, what's he going to do? He's going to have a constant color, which we'll just call 0. He's going to iterate over our width and height. So we're going to say for y in 0 to self.height, for x in 0 to self.width, we're going to do the same offset calculation. And we're going to, maybe we're going to say, so this is y and x, sorry, not row and call. And we're going to say that we take this address, we add the offset, and we cast this to a uint32, because we know in our specific case that we're 32 bits. And we're going to write, we're going to write our color. Now, I'm intentionally not doing a write volatile here because I want Rust to optimize something out, but we'll maybe compare with a write volatile after. So here, now we can say that the draw took this, and let's try a clear now as well. So we'll say start and end here, and we'll call framebuffer clear, and we'll say clear took this. So this should give us like a good clue. Right, so the fact that this took, like, the clear took literally 0 time and the draw took 300 milliseconds, this is like, it's happening so quickly that we can't even tell it happened with our 256 hertz clock. So that's like a really good sign that we will get to the point where we could, in fact, draw fast enough. And what if we do like non-release? We were do it in debug. In debug, it takes 9 milliseconds, which isn't, or is that 90? 90 milliseconds, which isn't great, but that is like a, what do we have? We had 12 seconds-ish, maybe 12, 13 seconds. Yeah, 13 seconds divided by 0.093 seconds. So it's like a 140 times speed up almost, which is pretty massive. So that's a pretty big clue that what we're doing is like fucking stupid, right? And let's think about like what the overhead would be. We would kind of assume that the this. So how can we say? There's like two obvious sources, right? There's this like x squared minus y squared stuff that could be taking some time, right? Some float math. There's also this like set pixel on every iteration is also maybe kind of slow. So we can start kind of like poking into that. So let's say that we've timed the original function now. We're at like 1345-ish, and like we'll just say this a little late. We've made an efficient clear function at also around 1345. And now we want to start looking into like potential optimizations. So the first one we said was setting a pixel or function call overhead / optimization issues, or in sphere calculation. Okay, so let's how can we do this? The easiest thing to do here is just replace our clear function with self.setPixel yx 0 0 0 0, right? The idea here is that if this function call overhead is like nasty, then the clear function will all of a sudden get really shit. So we can cargo run release. And our clear is still quite quick, actually. That's surprising to me. I thought that that would be quite slow. Cargo run. There, the clear got much, much, much slower in debug, but in release mode, it must be figuring out how to optimize that. So maybe it makes sense to try to like, maybe we can accumulate the time that we're spending in frame buffer setting versus color calculation. But unfortunately, our clock isn't like high enough resolution to do that. So I wonder how we can like maybe if we make like a vector of in spheres. Oh yeah, that's what we could do. We could start by we pre-calculate the in sphere values, and then maybe iterate over that list of in sphere values and put them into the frame buffer one by one. And that might give us a little bit of a, we could like maybe bisect where the time is coming from. So what we can do is we can say, let in sphere values is equal to a vec with capacity self.framebuffer height times self.framebuffer width. Capacity is what I'm looking for. And then I need to convert this to a usize, even though they're the same in our implementation. And then we push each of these instead. So we say in sphere values push in sphere. And then here we say let in sphere is equal to in sphere values y times self dot frame buffer dot width plus x. And this has to be converted to a usize. Okay, so now we can say that the in sphere calculation took this much, and draw took that much. Okay. So maybe cargo run release so that we can speed this up a little bit. Okay, so here we have in sphere calculation took 215 milliseconds, and the draw took 270 milliseconds, but I didn't reset the start, so this is actually 270 minus 215, which gives us like, we're dominating our time with the in sphere calculation. But the draw also is taking not like a significant portion of time. We should start with these this, right? This is like the obvious thing to speed up. And so some of the things that we're doing here is we're calculating these we're calculating some things multiple times, I think. So here we're doing I guess this has to be done every time. So because we have the x is changing over frame buffer width minus center x, but maybe this like floating point math is not doing so great, or maybe there's a way to like speed this up. So let's think about this. Okay, so what we can maybe do is start looking at the Rust playground and try to look at like the disassembly of this guy and see if there's any like obvious problems. So we could function test. And in here, we put this guy. We need this vector back. So here we had this guy. And here he's not going to build because there's like a bunch of stuff that doesn't true. So we can't use self.framebuffer. We have to say let width is equal to 640. Or maybe we'll take in width and height as inputs to the function so that the compiler knows that they're like runtime variables. Right? And then we can replace all of these heights with height and width with width. And here we replace height with height and width with width. And then we have one more here. Oops. Here we have, oh my god. I'm so used to being in Vim that like trying to select text with the mouse is like hell for me. Okay, so center X as well we need. So center X is U32, center Y is U32. And radius is also, radius I guess is a, oh sorry, this is a float. This is a float. Because where those are in normalized space, and our radius is a float. Can we look at the disassembly? I thought there was a disassembly output here. Is it Godbolt that lets me do this? Online Rust ASM. Maybe it is Godbolt. That's my bad. So here we want to use Rust somewhere, so Rust? No. This is only C++. Is there like Godbolt for Rust? I swear I've seen this before. It does say that it supports Rust. Oh, here, I have to write Rust over here somewhere. Here we go. Okay. So what's the problem here? No assembly to display, 6 lines filtered. Does this not compile? Oh, maybe I need to like make it public so that it knows to not remove it. There we go. Okay. So what the fuck is going on here? Can I like jump to these lines? Holy shit, that's a lot of code, man. Is there like opt level 2? 3. What optimization level do we use by default in Rust? I think it's 2. Okay. Okay. So divs ss floating point blah 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 blah. This is looking like quite complex to me. Quite complex. Like the fact, where's the loop? So my first thought is that this is causing a lot of extra complexity. So I wonder what happens if I just take this out. Take out the vector pushing. Maybe here that's stupid because the compiler goes like, uh-oh, you're not doing anything with that. That's stupid. So here we actually have to return like a vec of bool, unfortunately. And here we have to return in sphere values. And Compilation failed. Where's the compilation output? Click or drag output. At the bottom of this window. Output. Ah. Right, so this is only one E in sphere values. Okay, and now it's possible that it's like skipping a bunch of stuff still. So maybe what we do is we try to we go back to in sphere values dot push in sphere. And does this tell me anything interesting? So my first thought is that there's a lot of code in here, like a lot, right? Which might be indicating that, like maybe we are doing a lot of extra work to push the vectors in, push the items in. So maybe we can say, I think there's a way to like write to a slice that's pretty efficient. Maybe we can say like in sphere values as mute pointer or something. Yeah, okay, and we'll make this an unsafe function. And let's just like write to this pointer manually for now. So we'll say p dot add y times height plus x dot write in sphere. Hopefully that gives us something interesting. So compilation failed, so let's just see. Warn type var behind raw pointer. This is like such an annoying visualization here. Expected U size found U32. So here we obviously have to cast all of this to a U size for this add. It doesn't like that oh God, I hate it when editors like fill in stuff for me. That so pisses me off so much when they like put a closing brackets when I didn't type it. Just type what I wrote, please. Please. And maybe we'll take in the vector here too to try to like reduce the amount of like code in the function. So here we can maybe write to in sphere values directly and not return it. I accidentally deleted a squiggle bracket here. Okay, here we go. So this function's much shorter. Okay. And I wonder if we turn on optimizations here, if we can actually like understand what we're looking at. Compiling. All right. Okay. So how do I know what I'm looking at here? CVTS converts a single double word integer. The convert from source operand, blah, blah, blah. Yeah, this means nothing to me. Move DQA. Are these, so does this indicate that it vectorized? What are like move de quoi? Move align double quad word. So that kind of does, right? That makes it look like they're doing vectorized instructions. If they're using double quad words, that's a good sign. And I think that all these like XMM registers also indicate that actually. Let's see. I think there's like XMM registers. Registers of x86. I saw that somewhere here. Yeah, so basically if I'm seeing XMM, that's like mwah, SIMD. Thank you, baby. Okay, so that's a good sign. So let's go back into our original thing and try to use like a pointer here instead. So we can say let p is equal to in sphere values dot as mute pointer. And here we say p dot add y times self dot frame buffer height plus x. We convert this to a usize like we did in the other one. And we write in sphere. Then at the bottom of this loop, we just have to set capacity or set len to the new length, which is its capacity. And this is unsafe as well. But this may, like, we can see if this like heavily reduces the time. I think it will. Cannot call a method with a raw pointer in without an unsafe, but I'm in an unsafe. With an unknown type. Oh, I see. So P has to be a star mute bool, I guess. Okay, so that looks like it's compiling. And in sphere calculation took 200 milliseconds. So that's not really any better, which is kind of surprising. So another potential thing that might be causing problems is that the width and height might be too complicated for it to comprehend. So maybe because like in this version we had width and height. Actually, let's look at the disassembly to see if we see the same thing. So we can say target release kernel, and this is actually going to be impossible to find because this draw circle is not going to be named something useful. Fuck. I guess what we can do. Fuck it. Let's like just guess first, and if just doing a couple guesses doesn't get where we want, we'll like factor this out into like an actual function, and that will that'll help. Yeah. Okay. So let's see. First, let's just make sure that the vector allocation isn't taking up a bunch of our time. So we'll just move the timer a little bit down. So insert calculation is still taking a long time. It also looks wrong, by the way, but we'll we'll deal with that later. So here, how can we like reduce cost here? Let's try to cache the width and height, because there's a chance that like it's still doing these function calls over and over again because it doesn't understand that they're not going to change, which would be reasonable, right? If let's just quickly look at this. No, it should know. It should know because these should turn into U32s, but maybe not, right? So let's try. We cache the width and height. So this guy turns into height. This guy turns into width. This guy turns into width. This guy turns into height. This guy turns into height. And let's see if that's any faster. That got a lot faster, actually. Before we were sitting at like 20 or 200 to 170 milliseconds, and now we're down to 100 milliseconds. That's a lot better. But still doesn't seem great to me. It's possible also that we could gain a lot of time by changing these floating point things. Maybe we do less floating point math, do more integer math, and that fixes us up a lot. So maybe, how can we do this radius calculation in integer space? So we should convert center x and center y to pixel space. So say set center x pixel space is equal to center x times width. Center y pixel space is the same thing, but for height, right? Because this is like a float. These need to get cast back to U32s. Okay, and now we can do, instead of x over width, we can just do x minus center x. and center X pix. Sorry. Now the problem is that these are actually going to be unsigned, but we're doing subtraction, which could go negative, so we need signed numbers. So let's just cast everything to I32s for now. So we do the same thing here. We do y minus center y pix. And now we need to convert the radius to pixels as well. So we'll say let radius pix is equal to this is actually kind of interesting because this is actually different for width and height, but for now we'll just say it's the width squared. Sorry, it's radius times width as f32 cast back to an I32. There we go. So then we have x squared, y squared is an I32, and we need to just use rad pixels here. Cargo run. In release mode. Oh, baby. So we're down to 0 seconds there. Now, does this look correct? No. But do we see the ball bouncing around enough that we think that there's something in here that is correct? Yes. So that makes me pretty happy to see that we just saved like 200 milliseconds per frame or something. Like something absolutely stupid. And right, we got down to 3 milliseconds. The draw is still taking 80 milliseconds, so that's something that we're also gonna have to optimize. But we saved so much fucking time just now by doing just like a few simple tricks, right? I think the gist of it was not doing floating point math, right? We just convert everything to integers up front, and everything just gets basically free, which is sick. So maybe what we do now is maybe we try to pull out, like, remove this in sphere value stuff, because since we know that the sphere values calculation is taking like insignificant amount of time, like 3-4 milliseconds, but that's actually just one tick, right? Our resolution is around 4 milliseconds, so maybe it's taking 8 milliseconds, but it's slow enough, it's fast enough that we don't care anymore. So we can just we can remove this like extra complexity that comes from using this pointer and caching the sphere values and stuff, right? We can just say, we can take this draw loop and put it back up here. And there we go. So we cast these to U32s, cast these to U32s. Okay, cargo run. Okay, that's already so much better. That's already so much better. So here, our draw is taking like 50 milliseconds now, which is still shit, right? Not good, but much better. Now, I don't understand why it's flickering. That's a problem. Oh, probably because of this clear. Right, we wrote this like fast clear up here, and so we're probably flickering because we're clearing and then drawing and then clearing and then drawing. So let's just delete that. Yeah, and that's looking a lot better. Now let's think about a possible problem here is we could also possibly be destroying our performance with this here. In fact, we know that our performance is not good here, right? 50 milliseconds, not great. Yo man, what's up? Hey, we're just trying to make it so that we can draw shit on the screen, not incredibly slowly. So we've already gained what? We got from like, we were at like what, 250 milliseconds? Okay, let's see. Hold on. Let's not lie. Up here we have somewhere where we have logs of it taking a year. We went from 320 milliseconds down to 5, so that's a 64 times speed up, which is pretty sick. And we're trying to get it down a little more. So we have this like demo where we have this like ball bouncing around the screen, and I just want it to not be so stuttery. So that's L. Okay. So actually, this took me out enough that I should say that we speed up in sphere calculation. In sphere, I keep calling it sphere because I'm like used to 3D, but circle is the 2D version of a sphere. I've been here before. And we did that around like 40 minutes in. We'll say ish so that I know later that I have to find an exact spot. And now let's look at function call overhead. So we know that we can clear the screen fast enough that we don't even notice. And we could probably guess here that these like set pixel calls are converting from like float colors into integer colors on every call to set pixel, even though we have like a fixed color value. We could also maybe guess that this like isn't being inlined to the point where we want it to, right? Like really this is a loop that's calling this code very frequently. And if the compiler isn't figuring out that this is just a simple like pointer setting of these values, then that's going to cause problems. If the compiler can figure that out, then we can like get auto vectorization, and it should be like damned fast. Like we should be able to get like almost as fast as like the clear version if our pixel colors are reasonable. Sorry, if like our pixel colors are like constant. So I think what I want to do is I want to try pulling out the color calculation and then injecting like a pre-computed color into this function. That should be making it a lot easier. BGW, I was lurking around and came across your stream, and maybe I can help you with your Twitch custom graphics even more. If you're talking about how my Twitch has the default profile picture, yeah, I haven't gotten around to it yet. But yeah, if you feel free to stick around and watch. I'm not really too worried about it. Yeah, I'm not really looking for anything right now, but if you're enjoying watching, feel free to stick around and ask questions, etc. Okay, so let's start with a calculate color, and we're going to like basically take in. So what we have right now, what do we have? We have colors coming in as RGB in float values. So these are going to be like R is in the range 0 to 1, G is in the range 0 to 1, and B is in the range 0 to 1. And this is getting mapped basically to the range 0 to 255. And that's like a cheap one-time thing to do. And once we have these, then these are getting like packed into a like into memory as essentially like RGB padding. So they're 32-bit aligned. Actually, it's BGR, if I remember correctly. So what we should be able to do is we should be able to take this like RGB, and we should be able to like pack it into a U32 and then set this as a U32 directly, right? If we have like a little endian U32 that's that would look like B or G shift left by 16 or sorry by 8 or R shift left by 32 or 16, right? Because we're little endian, the smallest byte is first. So we can like pack this into a U32, and then when we write the color, it should just be as simple as writing like doing like a single pointer write, and that should be pretty straightforward for the compiler to figure out. Yeah, so let's do this. We'll say pub function convert color, and we'll take in R as an F32, G as an F32, and B as an F32, and we'll return a color. And this color is just going to be a struct here. And it's going to be like a simple struct that has a U32 inside. And then we're just going to do oops, we already have a function called convert color, but we can delete that. I don't care about this. But the math here is correct. So we'll just make this little helper inside, and we'll call it like 2 U8 is equal, takes in a value and returns this, right? And then for each of RGB, we convert to a U8, and we'll just do this packing that we set here. So we'll copy paste this very detailed comment, right? Very clear to me in the future. I'll read this comment and I'll understand what it says. I won't. And then we can just say that we convert it like we said here. So we have a let color U32 is equal to 2U8B for the blue, or 2U8G. Actually, let's call this 2U32, right? Because even though these are single byte values, we want the output to be, well, that's fine. I was gonna say we want it to be 32-bit so that we can handle shifting easily, but this is fine too. We can just do this. 2U8 U32 shift left by 8, or 2U8R as U32 shift left by 16. Okay, so what doesn't it like? We need self in here. And we remove these calls temporarily because we're not using them anymore. This is going to take in a color. And oops, this takes in a color here. And this adder now is as mute U32, and we say adder.write volatile color. Pretty straightforward. Okay. So now we just have to like return this output. So we can say color U32. And there's just some brackets that are missing here. There we go. So now what we should be able to do, hold on, what's wrong here? There we go. Now what we should be able to do is we go back to our like main loop. We should be able to pre-calculate the color. So we can say let colors equal to the input color, which is RGB and floats. So we'll say let FB color is equal to the color, or self.framebuffer convert color. And we'll take in color 0, color 1, and color 2. Now we pass in the frame buffer color here. Like this. And we also need to make a black. So this is going to be 0 F32, 0 F32, and 0 F32. Right, and then here we can use this to be FB black. And if we cargo run release now, there are some issues. So one is that we don't have like copy, which is annoying on this guy. So we have to derive copy and clone. Now this compiles. Oh, baby, look how fast it is. Woo! All right. That's going fast enough now that we can't even measure it, which is sick. Which is maybe like an indication that the frame buffer might be how do I say this? I wonder if it's like vectorizing. It might be like inlining the set pixel stuff to the point where it's vectorizing, is what I was trying to say. And probably the way to prove that would be to like pull it out into its own function later. But that's clean, which is actually kind of nice. So, how do I say this? It means that it's fast enough that I probably don't have to factor out a function for drawing a specific circle or drawing a specific rectangle. This looks like it's just kind of like working fast enough. Now what would be interesting is if we take out the like sleep time in our loop, how fast is this fucker moving? Oh my lord! It's so fast! Wow. That feels good. Yeah, that's pretty sick. Yeah, it's definitely fast enough that I don't give a shit. I'm sure that there's more to do later, right? Maybe if we draw lots of things in a row, this starts to become a problem again. But yeah, that's fine. It would be nice to be able to like remove the tearing and stuff too. But I don't know how, like, you would have to detect when the draw loop starts, or when it like finishes, and add like render the frame buffer at that exact point. And I don't know. I wonder if there is like a refresh rate. Oh, there must be. Like my monitor is displaying at some refresh rate. We're recording at some refresh rate, and my draw is taking such a short amount of time that it should be doable. But maybe that's a problem for another day. Okay. So let's just leave this here, and we'll say it's fast now, and that's at around like 51 minutes and 20 seconds of the stream. All right. So I kind of expected this to be harder than that. I guess I have some cleanup that I want to do here in this like draw loop. We want the delta back in. Actually, like maybe this is fine. Right? Like let's pull out the start and end and drawing. And maybe this actually looks fine, right? We have center X, center Y. Maybe this should be center Y norm, and this should be center X norm, and this should be rad norm, just so that it's like clear what units we're working in. But after that, we have everything converted into pixels. We have these like caching of width and height. I guess we could probably pre-compute rad pixel squared, just to save a little bit more time. But other than that, that's looking pretty good. That's looking fine. So we'll get add u, and we'll maybe look at what we changed. We don't need this clear function anymore in the frame buffer stuff. So this guy's unused. We don't need him. And let's look at what we've staged again. So we have this like color conversion that takes like RGB normalized floats and converts it into a color. We have set pixel has been modified to use a U32 packed in directly. We have a little bit of a mistake in here where we need to be, we've hard coded in this 8 and 16 and stuff, but these should be shifted by self.info.b, or there's a value that tells us in like the multi-boot info how far we should be. So blue offset, here we go. Blue offset times 8. This is operator precedent, probably like this. And what doesn't it like here? Cargo check. Oh, that's fine. And we do the same thing here where we say self.info.green offset times 8. And here we have self.info red offset times 8. Okay. What doesn't it like? Cargo check. It's fine. Cargo clippy. What doesn't it like here? Oh my lord. Cargo build. Okay, so why was cargo check working? That's weird. Cargo check. Cargo clippy. Cargo run. Okay, that's pretty sick. So the debug version's still pretty slow, I think. But it's probably because we're like unconditionally sleeping for 30 milliseconds, and maybe we can just change it to sleep for the remaining time. Right, so in here our delta is this guy. But we want to say that the start for each iteration of the loop is monotonic time get. The end is monotonic time get. Our elapsed is equal to end minus start times self dot monotonic time tick freak. Let's think about this again. I have to do my little unit conversion. So we have ticks times ticks per second. We need to divide to flip the symbol to get it to seconds. So we have here divided by ticks per second, elapsed in seconds. We say that the delta, or let remaining seconds, is equal to delta minus elapsed seconds. And this is only if elapsed seconds is greater than delta. And then we sleep for the remaining seconds. There we go. We can run. And that's in release. Cargo run and debug. Oh, oops. I think I gotta think backwards here. Elapsed has to be less than delta. There we go. Save cargo run release. And there we have like a pretty smooth movement. And now we can do the same thing for debug, and we can see if that's also moving it around the same rate. No, debug is still quite slow, but that's okay. I'm sure there's improvements to be made here. It would be nice actually if we can just like force optimizations for this function, because we know that it needs to be fast. But we'll target that later. Okay. So we're trying to make sure that this is ready for commit. So all of this looks okay. This draw circle function change looks okay. I don't see anything crazy in here. Yeah, okay. So we can commit. And we can say performance improvements for rendering, for ball render. And what did we do here? We pre-calculated the color. What else did we do? We pre-calculated the color, and we switched to integer math. Switched from floating point to integer math. This combo should encourage auto vectorization and inlining, etc. And this is a speed change from 300 millisecond-ish to draw to around 4 milliseconds-ish. Very nice. Okay, so we are an hour in, which is probably enough time to start on something else. What I wanted to look at is if we wanted to make like a game, we obviously need some form of like input handling, right? If we wanted to make like Brick Breaker, you could like either move the mouse along the bottom of the screen or use the arrow keys to move the paddle. Which means that we need to like process input, which we have no concept of right now. So actually, let's write down that we're starting this now. Input processing. This is started at, we'll call that what we did just now is like clean up and commit, and that took us to around like 59 minutes-ish. Okay. So we have these, like, if we want to handle input, we can hope that there's a PS2 keyboard hooked up to the QEMU virtual machine. And if I look up PS2, I'm going to get the console. But I think if I look up PS/2, I might get the port. Fuck, I don't want Google Maps. I want images. PS2 input. Yeah, so it's these guys. And I think if I remember correctly, these are essentially like serial ports, like the same way that we're doing logging through serial. This also is a serial interface. And this is like specifically for keyboards. And I think that like in mice and stuff, and I think like nobody uses these anymore. I should check the back of my computer. But I think like recent motherboards just don't fucking have them because everybody uses USB. But I don't want to implement USB right now because it seems like it's kind of complicated. And this thing seems like dead fucking simple. Because I think what they do here is this is like hooked up into a microcontroller, like the same way, or microcontroller is probably the wrong word, like IC. In the same way that to implement serial, we don't have to like bit bang the line and like process exactly with like when the Y lines wiggle and stuff with our specific baud. If I look at like the implementation for our serial console, it's actually quite straightforward. We just write to this like IO space memory address, and like to transmit, all we fucking do is we write like the byte of data, like the character, to this like spot in memory, which is like so fucking easy, right? So easy. And I assume that if we want to handle input from the keyboard, it's going to be the same thing, right? We're going to have some controller on our motherboard, and we're just going to be like, yo, was a button pressed? Can you let me know? Thanks. Yes, that's what I want to look at. So if I remember correctly, I think I saw when we were looking at like interrupts, I think I saw like a table of common interrupts, one of which was a keyboard. And so presumably, this guy is like at some address, and I can like just read that address to get the value of the key that was pressed, maybe, or maybe like the last key that was pressed. And then from there, maybe we can get something. So PS2 controller IO ports. We have the data port, status register, command register. Great. I guess we have to hope that this like 8042 controller is what we're using in QEMU. So I wonder if there's a way to confirm that. QEMU 8042 PS2. QEMU PS2 keyboard. So here in the QEMU source code, they do have a PS2 driver, and it'll probably be easier to look at in the version I have checked out locally. So if I go to QEMU, I can probably look up ps2.c, hello, ps2.c. And I wonder here if this will like tell me the address that it's hooked up to. Read data. So what, they have like some device, here we go, PS2 device, where we can probably look up like define PS2 device. Interesting, I don't see that defined anywhere. Where is this? Maybe there's like a PS2 header. Yeah, here we go, ps2.h. Do they have anything interesting in here? Object declare type. So this is getting like kind of complicated. Okay, let's go back here and see if there's anything obvious in here that tells us that it is using, it's like emulating the controller that we care about. So they have raise IRQ S, so PS2 raise IRQ. This has like an IRQ number associated with it, where this is PS2 state. So probably somewhere there's like a struct PS2 state. Okay. And where does this IRQ get assigned? Somewhere they must construct these guys. And this is getting complicated enough that maybe just browsing the source code randomly is not the way to get what we want. So maybe we look up like QEMU PS2, and maybe like we'll get docs for it. PlayStation 2, that's not what I want. Device emulation. Well, let's just like YOLO and just guess. I know I'm certain that I've seen this interrupt fire, right? I'm certain of that. It would be, God, it would be nice to know. Maybe there's like if I read the QEMU man page. Is it man QEMU? Aha! They have PS2 written right in here, so probably there's like a PS2 keyboard that's by default. If I search for keyboard here, is there anything that tells me? No. Okay, so by default, there is a PS2 keyboard. And if I use USB keyboard, that overrides it and removes it. And I guess let's just hope that the PS2 is like this controller and plugged in at the place we spot. Plugged in at the spot we think it is. There's probably a way to test this. Let's see if there's maybe there's like a status register that we can read and check if check like the add like the name of the device or something. Nothing in here is very interesting. What about the command register? Ooh, probably there's like a write, read, back and forth that we can do. Something. Okay, let's see. Flush up above. None of these. Oh, determine if PS2 controller exists. This is exactly what I'm looking for. So before you use it all, you should determine if it exists. On some systems, it doesn't exist. Sure. And attempt to touch it can cause the system to crash. Sure. The correct way to do this is with ACPI. Fuck. I'm not gonna do ACPI. I'm not going to. Well, fixed ACPI description table. Maybe that's worth looking at. If it's fixed, then we don't have to do that like bullshit like language parsing that they have. Fadit OS dev. This is like fixed ACPI table. So here there is this shit. And probably PS state might be the one. And this is pointing to my entry in the root system description table. You have to find this is there's so much searching here. I'm just not gonna do it. Fuck it, blaze it. I'm just gonna assume that the controller exists for now. And we'll put a fix me in there to do auto detection. Perfect. I lost that page about the controller. Was it here? Yeah, here we go. So here we go. So that any PS2. So what are the steps that they're telling us to? Initialize USB. This has nothing to fucking do with it. But if you were to do USB, then you might need to initialize it first because it might interfere. Sure. Determine if the PS2 controller exists. I'm just gonna assume it does. Disable devices. So that makes sense. We don't want to like break our. Like, if we're, like, initializing, we don't want, like, an interrupt to fire in the middle of that. Flush output, sure. Because, like, maybe, I guess, like, what happens is the PS2 controller goes, like, 1, 2, 3, 4 when I click 1, 2, 3, 4. And those end up in, like, some buffer because, like, maybe I'm not responding to events, like, perfectly in sync. So it gives me, like, a value. And so we have to say, like, hey, let's, like, not hold state from previous boots or from, like, electrical garbage, etc. Set the controller configuration. So basically, like, there's some uninitialized parameters that we need to set. Perform controller self-test. Fuck it. Determine. I'm not going to do that. Determine if there are 2 channels. That's a lot of effort. I bet that I can skip a lot of this and just start reading some data. But I guess for the sake of correctness, I will start running through these as best I can. So we'll make a new PS2 controller or module. We'll pull it in. We'll say PS2 keyboard is like a thing that we'll initialize. Probably he's going to have like a constructor that returns himself. Maybe there's some sort of initialization issues. We know that we're going to have this, like, we're going to be talking it through like I/O ports, where I don't know if you guys were around when I was doing Serial, but the way it works is like you have like CPU, and this guy is connected to like memory controller, who is connected to like my RAM, right? Like the physical bits of memory. But then there's also, I'm not sure if it's like here or if the memory controller manages it, but there's basically like another line that goes to like I/O. And all of these like same lines that go to the RAM are the same lines that go to I/O. And these are just like connected to like some circuit, right? So like some of the lines will be connected to like the clock, and some of them will be connected to, in this case, PS2. And so what happens is, like, when we access these guys, we basically have like a switch here, and here, where like we pick which path we want to take. So basically, while I'm talking to the keyboard, I can't access my RAM, is essentially the trade-off that we're making here. And so what happens in the future is like some people, well, in the future, in the today's world, is people will like actually connect these guys through the memory controller instead, and they'll just like delete some of these lines, because they'll say like, well, you only have like 4 gigs of RAM, but we have like 64 bits of addresses. Like, what are we gonna do with the rest of them? We'll just connect with the devices, which means that you can like access other RAM at the same time, etc. So, anyways, what I'm have to set up is there are like, since these like lines go to specific chips, these guys have like specific addresses that have like the lines connected to them that like control reading, writing. And so what I want to do is I want to like reserve some of those addresses to avoid I don't want to like accidentally try to use the same device for multiple places and fuck up its state. So I have this like I/O allocator, and he's like a mute I/O allocator. He comes from my create I/O allocator like this. And presumably what I'm going to do is I'm going to like request some I/O. So I'm going to say like I/O allocator request I/O range. And let's see, what does this guy say that his I/O ranges are? There was an address list here somewhere. Controller I/O ports, 60, 64, 64. So these are these 32 bits? 2 I/O ports, 60 and 64. Reads and writes may be something. So data port is used for reading the data received from PS2 and or writing data to the PS2 device or the PS2 controller itself. It looks like, since they're not really saying anything about like size, I'm assuming that it's 8-bit an 8-bit port. Especially because they're like mentioning in here that port 61 has no keyboard, blah blah blah. So they're like talking about a port 61. Is there like data, like the data register? Do I need to assume that it's 1 byte? Data port. It's weird they're not telling me how many bytes it is, but we can probably assume. Or maybe in the data sheet somewhere it'll tell us. External links 1. Is this the data sheet? Why does that link have no title? Here we go. Somewhere in here, is it going to tell me that the data port is 1 byte? Input port definitions, output port definitions. Yeah, here we go. bits, 7 bits. Yeah, okay, so we can probably assume 1 byte. That seems reasonable enough for now. Okay. So we'll request these 2 ports that are 1 byte wide each. So we'll say this is address 0x60, 1 byte. And we'll say let data is equal to this. And we have the status command. We'll call it command. And we'll just know that this is also the data port, or the status port. So we'll just comment that this is also status. We will store these guys in here. So we'll say data is a IO. What was this thing called? IO range. And command is also an IO range. The reason that these are ranges is because, like, in some cases we have like 10 different ports that are like back to back to back to back. And we might want to, like, we also don't know like how wide they are, if they're like 32-bit ports or 8-bit ports, etc. So we kind of like say that we're getting a range of things, and you can read and write to these ranges. In these cases, the range is one byte long. Here we also need to call this an IO range. Great. And then we return a PS2 keyboard that comes with data and command. Now, here we probably need to run initialization steps. But maybe for now, let's just quickly look at these guys. So this has to be done in pre-interrupt code, I think. We don't want, like, or we disable interrupts while we're doing this. We could disable interrupts. So we have this, like, interrupt guard class. So it comes from crate, like our kernel crate. We have, I think it's interrupts. No. This comes from somewhere. It's util interrupt guard. Here we go. So we have like this like mutex-esque type that says like, while I've got this like guard, don't fucking, like, I'm mutating some data that interrupts could like fuck with. So we can say that like let interrupt guard is equal to interrupt guarded new, and it's like nothing. We're not actually guarding some data. We're just trying to use this as a flag. And then we say let interrupt guard is equal to interrupt guard lock. There we go. So now interrupts are disabled. And so that's this stuff. So we start by sending this guy to the PS2 controller, 0xAD and 0xA7. So what do those do? What do those do? Command byte. I already forgot them. Fuck. I already forgot them. 0xAD and 0xA7. So AD doesn't exist. Oh, it's down here. Disable the first PS2 port, and A7 disable the second PS2 ports. Only if 2 are supported. Okay, sure. So we will send out 0xAD and 0xA7. This is a function called disable PS2, and this takes in the command range. So we'll just shove this guy down here for now. And this needs to be written at these are all going to be written to offset 0 because there's only one item in here. Which needs to have the strong type IO offset. So like this. And now we need to like use this IO offset shit. Like this. Okay. Now this guy can fail, right? Because if we write these U8s, then we might be out of range. But we should be guaranteed to be in range at this point. So we'll say unexpected out of range. during, we'll just call it this. That's fine. That's fine. And then here we can call, say, disable PS2 with the command register. Like this, easy. Okay. So what's the next thing I want to do? Flush the output buffer, which is just pull status register or read from IO port 060 without testing bit 0. Pull blah 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 blah. It could be good to flush the buffers. Control. There's two ways to do this. Pull bit 0 of status register. Or read IO port 60 without testing bit 0. I get, like, what are they talking about? Do I need to, like, is the output buffer, like, large enough that I need to pull it multiple times? Somewhere they must tell me output buffer. There, I would assume that there is a buffer in case I'm not reading them fast enough, but output buffer. They are saying that it's either full or empty. So full with byte from first PS2 port. Yeah, okay. So it's kind of claiming that there's only one byte. So we'll call it like read output buffer. And I assume this comes from data. And we'll discard this. And probably, like, is there really, do we really need to make a function for this? It's probably worth naming. So this is data, and it's a mute IO range. And this is just a read U8. So this is data, read U8. This returns a U8. And we don't write anything. We just read this offset 0. And we don't return. There we go. Okay, so now this guy has to be mutable so that we can access him. And there we go. Now we can set the controller configuration byte. So let's look at that. Does it tell me status register? Configuration, baby, command register, configuration byte. See below. Here we go. So we want to enable the first PS2. We want to disable the second one. I want to post. It says 0. First PS2 port clock. Whoa, what the fuck is port clock? Like, what does that mean? Port clock. I guess clock. Nothing is really telling me what that means. All right, well, let's see what this guy tells us to write in here. He says, set the controller configuration byte. Because blah, 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 it means reading the old value back, changing the bits, or reading the change value back. Command 60. You want to disable all IRQs and disable translation. While you've got the configuration byte, test if bit 5 was set. If it's clear, then you know it's PS2 dual channel, blah, blah, blah. Okay. Clear bits 0, 1, and 6. Okay, so what is he saying that it is? 0, 1, 6. All right. I don't understand what this clock is, but he's saying, like, read it and then change right back. He's not saying to change the clock at all, so sure. So we'll say we'll say that we're gonna like initialize command or initialize config register, and this comes from command. And we'll say function initialize config reg, takes in the command, takes an I range. And what's he do? He says, bum, 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 bum. So I read it, which is a command. How does this work? So can I read configuration byte? So how do I read it? Here, read the old value, command 20. Okay, so that's 0x20. So read byte 0 from internal RAM. So does this come back on the data port? To send a command to the controller, write the command byte IO port 64. If there is a next byte, then the next byte needs to be written to IO port 60 after. If there's a response byte, then the response byte needs to be read from port 60. Okay, cool. So this guy also needs the data port. And so what I do is I say, I write the value 0x20, and I have my little assertion here. And then I read the value back here. And this should be the config reg value. Now I should be able to do what it says, which is disable some of the bits in here. So he wants me to disable interrupts. So I can say config reg value disable or set bit, which I want to disable the first interrupt, the second interrupt, and translation, which is 6. And I think that's what he said to do. And then this must be 0, this must be 0, and I won't change the clocks. And system flag 1 should have passed post, sure. Okay, cool. So I need to import my like bit manipulation stuff. So I can say I have like a util bit manipulation get bits, or I guess this is set bits. And then I just call initialize config reg with the command and data registers. Cool. Cool. This should be public, by the way. Cloud function. And we'll keep moving through this guide. So what do they say next? Determine if there are self-test. Determine if there are 2 channels. Perform interface tests. Enable devices. Here we go. So actually, I can just like immediately enable the interrupt. Because I'm just skipping all of the actual stuff that they asked me to do. And that's on the reset. So, do they actually tell me what to do here? This is, just send a byte 0xFF to each usable device. And it will respond with FA or FC. Okay, so here I just send FF to a usable device. Which is a command for the device and not a command for the PS2 controller. To send the reset, just send byte FF to each usable device. So I guess that means I just write FF to data. Probably. Yeah, nothing in here saying anything crazy. And I guess I need to enable the PS2 port. So I have to do 0xAE somewhere. Did I miss that? Oh, enable devices. Here we go. So here I send 0xAE. So here we'll just call this enable PS2. Here we copy paste this disable function and call it enable, and this becomes like AE, I guess, and A8. But I'm not going to use the second port for now because I don't really care about it. And I'm just going to hope that the first port is the keyboard. Reset devices. So I guess how would I choose which device I'm writing to? Read controller output port. Write next byte to controller output port. Write next byte to PS2 port output. First PS2, second. So I guess I run D1FF must be what they mean, right? I want to like say, I want to write to the controller output. And then I'm going to send my value. Let's try that. So we'll say function reset devices, which is command takes in command IO range, and data, which is also an IO range. And here, if I'm reading this correctly, I should be able to write 0xD1 right there. And then I should be able to write to the data port a 0xFF. And I have no idea if this is right, by the way. We'll see. Okay. In main, we're going to initialize our PS2, which is a PS2 keyboard. We have to import this, so this comes from create IO PS2 keyboard or something. This has to be public, or else it won't work. Oops. And then here we need to like actually create it. So when we construct our kernel, we say let PS2 keyboard is equal to PS2 keyboard new. When we pass in the IO allocator, and this is called PS2. All right. And now the question becomes, how do we validate that this is right? So I guess what we can do is we can poll the data port. So we can say like pub function read. This will return a U8. And we can just say self.data.read, or this takes in mute self, and he's going to be read U8. No offset. And we can just unwrap this for now. And maybe what we do is we create like another future, like another loop somewhere that will happen in parallel. So we'll say let poll keyboard, right? He's like an async block that loops, and he sleeps for some period of time, maybe like 1 second. And in between each sleep, he just prints read this from keyboard. And then we'll just say ps2 self.ps2.read. And then we should be able to see if we start typing, if we start seeing different values come in. So weirdly, I'm not seeing anything. Okay, here we go. So when I'm typing in here, nothing's happening. That's weird. Oh, because I'm not actually running this code. So let's just add it to the list of things that we're going to do during our demo. So here I'm getting 160, 159, 145. If I press S, I should get 159 again. And if I hit W, I get 149 again. Or 145, sorry. So this does look like it is in fact reading from the keyboard. Every time I click a key, I am seeing like a different value come in. And I'm getting like consistency from the value. So that's really good. Probably what I want to do next is I want to, instead of polling like this, I should probably say like, interrupt me when there's something to read. or maybe return an option from this guy and only log when like a key goes down or something. So in here, let's say that this guy, there's probably like a status register somewhere. And here we'll say that our output buffer status is empty or is full, right? We want to say if output status is full. So we say let status is self.command read U8 from offset 0, which is the only thing that we can read. We can say print line status. And we actually want to format this as Boolean so that we can like look at the flags. And let's just see what we get when we do this. So here we're getting zeros. Here if I type in here, I get that set to a 1 and then to a 0, so that's really good. We can tell by polling if a key was pressed, which is sick. What we can probably do is we can probably make this an async function, right? And he will only return, he'll like block until there's something to read, maybe? Is that reasonable? Let me think about this. Beep boop, beep boop. Yes, I think that's reasonable. I was thinking like in a game loop, what would I do, right? I would be running my game, and it's like if I have like a blocking read forever for keyboard input, that would be kind of like a shit show in synchronous code. But in asynchronous code, I can just like put like read and do other stuff. And when you get read, do like handle it, and when you get other stuff, handle that. And so I think that's actually totally fine to just block forever, which is kind of like a nice thing about this like API. But in order for like this to read forever, we actually need to first handle an interrupt related to this guy. So what we can do is we can say, please give me our like interrupt controller. I think it's what we call it, interrupt data. And this is a like interrupt handler data, which I think comes from interrupt handler data. And we can just request once we're here, we can say interrupt data register. And this is going to come from, I think it's IRQ1 is what I read. So we can say IRQ ID from pick1 value 1. And we'll take in a function. And I think all this is going to do is like for now say print line got key press. Just to see. So now in main, when we construct this guy, we need to pass in the interrupt controller. So here we just pass in interrupt handlers, I guess is probably what I called here. So probably here I should call it interrupt handlers for consistency. There we go. Let's cargo run and see what we get. And so here, if I... Okay. So it says got key press a lot. And now I print here and it says got key press there. Got key press. Got key press. Okay, sick. So every time I press the button, it says it got a key press, which is really sick. And now all I need to do actually is if we had like proper piping of our futures, this would actually be a lot more complicated. We would have to say like, hey, wake up this specific future when something happens. But what I can do instead is just say like, fuck it, wake up the executor. Because all of our futures internally use like the same mechanism of being woken up, which is that like we kind of like sit in this state where our CPU is just doing nothing, and then an interrupt triggers, and we go like, oh, what happened? And we're like, oh, I don't want to wake up yet. I'm gonna go back to sleep. But if we set this Boolean, this atomic Boolean from inside our interrupt handler, it tells that our future executor that it's like time to do some work, and it will just like look at everything it has to do and be like, which one of you fucking things is done? And so all we have to do is wake up the executor here with I think it's like future wake up executor. And And then here we can make this like an async function that pulls the status register. So we can say we make like a pull read future, and he has like a lifetime because he's going to take in this this status register by reference. So we're going to say status is a reference to an IO range, probably a mutable reference actually, who needs the lifetime set before mutable. And then all we have to do is implement core future for pull read view. And his output is going to be nothing. He has nothing, like he's not actually going to read the value. He's just going to let us know when it's ready. And all he has to do is run this. And check if the status bit 0 is set. And if he is, he says that he's ready to go. So it's core task pull ready. Otherwise, he's not ready. So that's else pending. We forgot to add the lifetime here. And this is status, not command. And we need to add this like get bit helper here. And that's literally it, right? So what will happen now is, oops. Let's make this guy underscores that he doesn't get angry. This needs to be borrow self as mutable since it is not declared mutable. Uh-oh. Why is that not working? Can I write mute here? Cargo check. Okay, that compiles. Right, so we're actually kind of like, all we need to do now is we construct this pull read future. With status is self.command. And we wait him, and that's it, right? Now we're not going to read anything until it's time. And so here I can actually make this an async function. And then back in my main where I'm like polling the keyboard, I should actually, instead of having to sleep for 1 second every time between them, I should actually just be able to get the value like almost immediately, right? All this is like print the value from the keyboard. So let's see, I'm gonna click it now. So there are some like spurious interrupts in here, but that's actually looking like pretty damn good, right? If I like start like spamming, that's pretty good. Pretty good. So now maybe just as like our like simple demo, maybe what we'll do is we'll just pause the animation if I press any button on the keyboard, or maybe if I press spacebar, 185. Okay, so let's do that. We'll just say that here in our drawing loop, let's think about this. So normally what we would do is we would maybe like make this loop one async chunk, and we'd make this keyboard pulling another async chunk. But maybe what we can do is we can actually just pull the future manually here. So we can say like futures, future pull immediate. And we can pass in self.ps2.read. And we can say if this is ready, if let some value is equal to this, we sleep theorem the delta. We sleep for I guess this what we would actually do is we would set the pause state. So we'd say let pause is equal to not pause. Easy. And then here we'd say if pause, we sleep for delta. Like this. And now we just need to make a thing pause. So we say this comes up here. Let mute pause is equal to false. where we've got like a slight mistake in here. So expected poll immediate output U8 found option thing. We forgot to await this, right? Obviously, this. And down here, we delete this pull keyboard stuff because we don't need it anymore. And yeah, I think then we continue this loop. So I think now, I guess we also want to say if V is 165, I think was the value we got. Oh, 185, sorry. Okay, so let's see. Oh, baby. Look at that. Pause, unpause, pause, unpause, pause, unpause. That's sick. Okay. So there's obviously more to do here, but I think that we've kind of gotten to like a kind of nice spot here where we're seeing that our animations are nice and smooth. There's a little bit of tearing still, but that's okay. And I have like input control handling, which means that if I wanted to write a game, we're like very close. The only thing I'm really missing is I don't know if a key was pressed or released yet. But other than that, yeah, that's fucking sick. I think that maybe if I hold it, it might just keep spamming. So maybe I can like print line hi. Oh, no, it's only on release, it looks like. Okay, so there's something to do there, where we need to detect key down events if we wanted to make a game. But overall, that's pretty sick. So I think I'll call it there for the day. Pretty happy with that. So yeah, we got to the point where we did some like heavy, I will say heavy, we heavily improved the performance of our rendering of the ball bouncing around. It was actually pretty straightforward. It's just like, you know, try to avoid function calls that aren't like easily inlineable. Try to make sure that you're not doing like extra calculations when you don't have to. Try to make sure that you're using like integer math over floating point math when available, that kind of thing. So we like, you know, pre-computed some stuff. We got like vectorization coming out pretty good. So that was working okay. And then once we got that sped up, then we added like input handling. So we like wrote like a really like the world's shittiest PS2 controller, where PS2 stands for not PlayStation. I actually don't know what it stands for. Does it say here? PS2 port. Does it not have a like name? What does PS2 port abbreviation? Personal System 2. Okay, so we've implemented Personal System 2, like the world's shittiest Personal System 2 driver, which can read when keyboard events happen, and we like do something with those keyboard events, right? We're pausing our like little demo video when that happens. So nothing too special, but I'm pretty happy with that improvement. So probably what we'll do next is try to like hook all this together to make some form of like shitty game, right? It'd be kind of fun to like make like a little Pong or Brick Breaker or something. So if you want to see that, you can tune in tomorrow. I think that this like 1 o'clock streaming is kind of working better for me. So if you want to tune in tomorrow at 1 Pacific time, that's when I'll be live. And if you want to catch up on YouTube, the YouTube is linked in the Twitch description. If you're on YouTube and you want to catch me live, Twitch is linked in the YouTube description. I guess I'll quickly just post a link to the source code here in case anybody wants it. So github.com/spheraphoria stream OS. And I'll also post this in the YouTube description if anybody's curious. So thanks for watching. Catch you on the next one. Bye.